complete the pictures a bit more before we go into that. This actually comes in two other data dependency issues. So we previously said that is read after write. So we're just saying, oh, if I have R1 and R2, I don't know, R2 plus multiplied by R3, R1 may have to be fetched later plus R5, and there is a data dependency issue. Is that I have a read immediately after write. But then actually, if you have a varying length, now things become quite interesting because instead we have write after write issue and write after read. I'm gonna explain why that's the case, but let's just talk about these dependencies first. So if I have I don't know, R1 R2 times R3, and then R1 R2 plus R3. Yeah. So there's no data, there's a data C dependent. So if there is read after read, it doesn't really matter because I'm not tempering anything about it. Everything only comes in if there's a write and there's an issue. Because read after read, you don't really care about it, isn't it? So write after write, it's here. So if you have write after write, then how's that an issue? Because it doesn't seem anything. It doesn't really seem any wrong about it, isn't it? Because nothing is really doing anything. Like it doesn't, like for sure that my second instruction is gonna overwrite my first instruction. Yeah. So so pretty much in the write after write and write after read in the basic 32i setup, as we keep talking about, that was not always an issue. But those issues only comes in when you have a varying length sort of pipeline. So maybe I have a pipeline with execution stage of 7 and the other one will have 5 or maybe 3 or something. Now there comes the issue. What about write after read? Write after read is like if I have again R2 times multiplied by R3. I kind of forgot what write after read is. Oh, okay. Maybe I have I think this probably have to do with the low word. And then R2, I don't know, something like that. Low word R2, so maybe I'll just say mem. Something like that probably. And then I'll just say, I don't know, I'm gonna write R2 to be R1 plus R3. So as you can see, now there is a write after read. The write after read actually only comes in when you have a varying length of memory operation. So the memory operation, remember that in our basic assumption, it's just one cycle read, just one cycle, like one cycle sort of memory operation, read and write. But then here comes the issue when you have varying length. Maybe your memory is internally pipelined, so maybe there is a memory 1, memory 2, memory 3, memory 4, that sort of thing. There might be an issue when you have such thing. And to be honest, I don't really know that much about the write after read just yet because my out of order doesn't really study. I don't really study out of order until the only the execution unit. I haven't really studied out of order of the memory part just yet. Okay, but anyway, let's just talk about write after write and write after read. How's that a case? So again, let's talk about the idea of out of order. So out of order, I pretty much just want to swap the instruction around, right? So if I take a look at this specific case, so just zoom in and see what happened. So maybe my setup will be E1, E2, E3, E4, E5, E6, and then what is that? M right back, and then F, D, E, M, W. So the above one is pretty much my multiplication, and then the bottom one will pretty much be my addition. And okay, so this is the case where I assume that there's no in order retirement. So I'm going to talk about the reason why write after write becomes an issue. It's because, think about this, is that okay, so if I don't have a in order retirement, so here I'm going to talk a little bit more about the sequential model of the von Neumann. So pretty much think about this, is that if I have a write after write issue, what actually happens is yeah, over here, my R1 is updated in the register file by R2 times R3. Over here, my R1 has been updated to R2 plus R3. But let's take a look at the timestamp. Yeah, this is the case. That's the correct one. But then later on, my previous instruction overrides my second instruction. And now you can see that in the very length, my right after right becomes an issue because I could have a later stage. I could have a previous stage that is still running overrides the completed version of my later stages, later instructions, such as this. So in the end, you're gonna find that if I have the right not sequentially executed, sorry, if I have my right stage not sequentially aligned, then you'll have this overriding issue from up to a plus R3 and then being override by the previous results. That's bad. So yeah, that's bad. So this, hopefully you can see that this is the case. And to be honest, the right after read, I don't actually know. Maybe instead, if I zoom in this problem, it could be like something like, I don't know, E, and then M1, M2, M3, M4, da da da, and then right back. And then you have F, D, E, M, right back. I actually don't know. I kind of forgot, but said that if you have a cache or something, and then maybe upon here you have cache 1, cache 2, cache 3, and then you then get the result for the register. I actually don't know that much. Yeah, so sorry, this one I couldn't really provide you any practical example, but I guess you have to look into like the memory internal pipeline and see that, oh, since when's the case, maybe my memory itself, right, could fetch a wrong R2 that's been, like, maybe your R2 has been updated and then you pass it into the memory, which supposedly your memory has to be fetching like a old non-tempered R2, but then your R2 has been updated and you now reached the new value or something, and now there is becoming an issue. So yeah, so you can see that now there is a bunch of issues I just introduced with varying length setup. But we kind of talk about how varying length is a natural decision, because if I don't do that, and if I just put everything just like crumbled together in one sort of stage, and essentially that it's going to dictate the entire pipeline, isn't it? So in that case, it's naturally for us to put this into multiple execution stage. But then now you have a trouble, which is like a bunch of like right after write and right after read issue. So yeah, this is the point where I'm going to start introducing the register renaming, which is here. And this is probably the most beautiful thing ever I have seen in it's probably the most beautiful thing I ever seen in computer architecture. I did say that for my branch prediction, but this one's more beautiful, like more beautiful in my opinion. Okay, so I'm just gonna copy this setup and let's talk about what register renaming. So, in just a bit of spoiler, register renaming solved the issue renaming. So if I can have this renaming idea, which is what you can see in here, when you have the queues and maybe you have the decoder and so on. I don't actually know that much about the internal things in the boom, but I assume that the queues is probably the reservation station, and over here I maybe have the sort of sorry, actually I should pull up another table with another file, which is this. Yeah, as you can see, my setup over here. Yeah, there's a mapping table, which is yeah, here. So if I can just have this rename, so I'm going to talk about what the idea of rename is. So decode, we don't know that, but then rename, what's renaming? Okay, so he's gonna come a very hectic example. So I'm gonna assume this the following example, and I'm using the same example as yeah, I'm gonna put that in the credit, which is I'm using the same one as I'm using the same example in this lecture, which is the this exactly the same. I'm just gonna go through that. So yeah, I have the following setup. I have this instruction. I have this one instruction, and I have also the scenario, which is saying take 6 cycles. And then also have an addition unit, which also take 4 cycles. Okay, so that's my setup. And if you actually read upon the if you actually read the table, not the table. If you as you can see, this is the paper. If I read the table, why do I keep saying table? If I read the paper for this bit, the efficient algorithm of exploiting the multiple automated unit by Tomasulo, you can end up seeing like the out of box. You can actually end up seeing this similar setup, which is having the different. So we kind of say that it's naturally to have. What do I zoom in? Okay, so it's naturally for us to have. I don't know. So I'm gonna have. Sorry, I'm having a multiplication unit. Where I have addition unit here, and I have a multiplication unit. And just to recall that it's internal pipeline, having 4 cycles and 6 cycles. All right. And then what happened was I'm gonna introduce something called register renaming table. So the register renaming table is pretty much the extension for my register file. But instead, remember how our previous register file is pretty much just okay. So this is my register file, right? So my register file, how does that look like? How does it pretty much just like I have like I don't know R1, R2, R3, R11. Well, you know what? I actually will put every single one down. R4, R5, R6, R7, R8, R9, R10, R11. Yep. So that's and then over here I'll put my data, right? So it's data, and R1 will be like 1, 1, 0, something like that. But then I'm going to extend the register file into the following, and I kind of forgot, so I need to pull this up, which is yeah. So I'm just going to say I'm going to have the extension, but we'll call valid, and also the tag. These are the stuff I'm going to have. So I'm going to have an extension, 2 extensions actually. One called the valid bit, and the other one called tag. And you will see the reason why I need that. So just draw a table, kind of looks like that. And then so this is the data, just so you know, value. So why do we need a valid bit in the first case? Because the valid bit is sort of like so every time when you have this dependency issue, I always want to put the valid bit into 0. Okay, valid bit actually comes with the RAW. So we have to write. So when you have to write, I know that I'm writing towards this register, so I simply put this valid bit into 0. So that's come with the idea for my even just the. So that's actually going back to the pipeline. So remember how we talk about data forwarding of store flush? Pretty much just solve all the problem, and not all the problem, but like lower the store, right? But then there's another way. This is the first way of doing it, and the other different way of doing it is what you call the register. You keep track of the register, so it's called a scoreboarding. So the scoreboarding is pretty much just having an extension of this valid bit, and just say that okay, I'm going to test against that valid bit. If I'm currently like if I have this read after write, then I can pretty much in my register file just set this valid bit until 0, and then maybe in my write back stage I'll update this one to be 1. In that case, I can just know that okay, when I'm fetching the instruction, so I'm reading this instruction, is that valid? If it's not, then I'm gonna wait. If yes, it's valid, then yeah, go on. There's nothing wrong. And then if I write back, I'll say that oh, now I'm writing back. The value has been updated. Good. I'm gonna set the valid bit back to 1. So yeah, that's pretty much the setup of the valid bit. So this is just a notation for just trying to solve the RAW, keeping track of whether. So yeah, is what not been covered in the lectures or in the Harrison Harris book maybe. It's called the register scoreboarding, and the register scoreboarding actually comes in the idea here when you have and there's a tag. So the tag pretty much It's similar to the idea. So you can see that valid bit and tag, it kind of looks like a cache structure. And where's the tag going to point to? So I'm going to have another thing called the reservation table. So sometimes people call this reservation table. Sometimes people call this queue. So this is probably like issue queue or something like that. Yeah. So again, I forgot what this setup is. So let me take a look at here. Yeah. So you have this. So you pretty much have a valid bit. So let's just say I have 4 different entry here. 1, 2, 3, 4. So I have valid bit, and maybe I have a tag. Okay, maybe I have the value. So I'll just do like that. I'll probably just color this bit just to indicate that there's a separation here. Okay, lovely. So the idea now is that I'll show you what exactly happened here. So the initialization comes in every bit as valid. Every register file is valid because it's initialization, and then every of my reservation table will be setting up as 0, 0, 0, 0. And as you can see, there's a symmetric happening between the left and the right. I mean, the left and the right is because I pretty much have 2 sources I need to deal with, 2 operand. So yeah, that's why. So tag. Sorry, what am I doing here? Here. Yeah, and I'm gonna initialize all my data as accordingly. Okay, so let's try to simulate it within using different cycles. So the first cycle I have fetch. Okay, so fetch I haven't. Just so you know, I'm putting every single. So the register file exists in decode stage. So is my reservation table. So yeah. Actually, they can be a design choice. You can put this in execution unit or decode stage. I'll probably put it in decode stage. So nothing happened in the first cycle. So and then I have decode of my first instruction and then fetch of my second instruction. Okay, so what's my first instruction? First instruction is basically just so I'm just gonna 1 here and 2 here. So first instruction is pretty much just R1 plus multiply R1 R2 to R3. So what I'm gonna do is I'm gonna use multiplication multiplication now, and there's an update between the sorry, let me just erase that. So I'm gonna write into R3. So I'm just gonna set my R3 into valid bit equal 0. So now this value, I know that it's going to be updated. So this value is like, it's like the old value. It's like the old value, so it doesn't really matter now. So I'm going to put this valid bit into 0. And then I'm going to say, okay, now I'm going to set up the reservation table. I'm going to set up the reservation table as follow. So there's issue queue. And I'm going to say, okay, I'm going to have this new entry, my multiplication, which is 1. So this, okay, sorry. So what happened was, over here, I'm going to have R1 multiplied by R2, right? So I'm just going to copy entirely my R1 information, which is data, valid, and tag. So valid and tag, I don't care about tag because there's nothing in the tag. Value is 1. And another one is valid, I don't care about tag and value. So pretty much you're going to end up, nothing, hang on, I'm going to talk about that later. And then over here, I'm going to call that address, okay, there's A, B, C, D, and this is X, Y, Z, W. Just to know that A, B, C, D, and X, Y, Z, W are the actual address. So they are the address for your reservation table. And then so my tag is now pointing towards this index, pointing towards this track, saying that, okay, in entry X, I have my results. Yeah, in entry X is my instruction. Oh, sorry, put the wrong place. It should be 3 instead. Yep, so that's pretty much the setup. So the procedures follow. The procedure is basically first clear the valid bit for your thing that for your destination register. And the next thing is you pretty much copy your operand from R1 and R2. Copy that. Yep, lovely. So that's the setup. And then I just know that now my valid bit is 0, and then I can find my tag in the X. Okay, lovely. So this is what you call the register renaming, because what happened was I used to call R3 to be the case, right? I used to call that I need the R3, but now I can actually just use the tag to reference to my data. So I can say that, okay, you want R3, the value is in X. So how about if I just call X like a new variable? Like what I mean was the idea, okay, so here I'm going to introduce the idea is register renaming. And the register renaming is comes in here. So output and anti-dependencies is pretty much just WAR, WAW are not true dependencies. So we speak about that like it's not true dependencies, but they only comes in when you have varying length stuff, and then they actually exist due to lack of register ID. So what I mean was like, for instance, pretty much previously what we said is, well, if I can just use different register, if I just use R5, then none of that issue will be here. But then we have limited amount of register, so always you're gonna have an overlap between them, isn't it? So if I have just infinite amount of register, isn't that kind of nice? Because I don't have any, I can just write to a different bucket every single time, so I don't have a write after write and write after read issue. So the read after write is, no matter how many bucket you have, you always need this dependency, because maybe I have like, I don't know, 3 plus 4 and then multiplied by 5 and then divided by 2. So you need this first, and then this, and then this. You always have to execute this sequentially. But then the write after write and then write after read is basically just lack of register ID, because as you can see, I don't depend on the results previously. So if there is no sequential required, then why is it that I'm writing to the same bucket? It's probably just because I don't have enough bucket to write to. So instead, the idea here is that I don't have enough register ID. So this is the lack of register ID. So if I have infinite amount of register bucket to write to, isn't that going to solve the WAR and WAW problem? Well, yeah, that's ideal case. But then in the real life, when you have the ISA pretty much dictates how many amount of register you have, and also the physical constraint as well, because when you have your register, it has to like, I mean, the accessing time is a bit, yeah, your accessing time will be a bit crazy, because like you don't want to access the memory, because register file is temporary, so you want your register file to be still small, not like infinite amount of bucket. But then, so the idea is that no matter what, you're always going to run into WAW and WAR problem, and the reason for that is pretty much just lack of register ID. But then you can see that now. Instead of using a key value pair, so if my key will be like R3, and then R3 will be having the value of 3. Instead, I can just call this key value pair, instead of having a tag saying, okay, now my new sort of storage, so the bucket is in X. So this X is my new bucket, isn't it? So my key value pair now becomes X and 3 properly. Sorry, X and its associated value after the computation. So it's not 3, sorry. So now this becomes a new key value pair, and then will have to come after this 6 cycle. So yeah, now you can see this register renaming is the idea. I renamed this R3 into the key value pair X and other stuff. So whether it is not R3 or not, it doesn't really matter anymore. It just pretty much everything is just yeah. So pretty much is creating like a new storage in the reservation table. So a new entry here, and then like you generate a new key value pair, so you no longer depend on R3. Like whether it's R3 or not, it doesn't really matter anymore, isn't it? Okay, so I'm gonna keep talking. So okay, so let's talk about third cycle. So third cycle is fine. So because my first instruction, so what happened was in the execution, right? What I will do is I'll check valid, wonderful. Now I'm gonna do execution, because both of my value are valid. So I'm not waiting on anyone, and my value are all valid. So I can just take the value and start execution, isn't it? Okay, so beautiful. So execution will just do its own thing here. The execution will just do its own thing. So yeah, so I put E1 here, and then I have decode of my second instruction. So the second instruction is pretty much add R3, R4, and R5. So again, let's just start with what I need. So R5 is being updated. So I'm just going to put R5 into 0, and then I'm just going to put a new entry in A. So I'm going to point to A this time. So this is now pointing to A. And I'm going to, again, copy every single entry in my R3 and R4 into it. So my R3 and R4 here. So my R3 will be, is it valid? It's 0 valid. So it's not valid at the moment. And then where can I find it? It'll be find in the tag X. So if I want to find the value of R3, I can find it here. So that's pretty much what the tag is for. Value, it doesn't really matter anymore, isn't it? Because my X will update later. Okay, and then what about R4? R4 is valid. So 4 and 1, and then, sorry, got it wrong. Valid, value 4, tag. So, okay, so in this case, I update it here, and let's go to the next cycle. So if I go to cycle 4, I have queue execution, and then, okay, here, can I execute is the problem. Okay, so first we have to deal with, can I execute? Again, valid and valid? No, because one of them, my R3 is basically, as you can see, still waiting on the previous results, read after write. So in this case, I'm just still waiting on the previous results. So I'm just going to put it as, I'm just saying that, okay, I'm checking valid bit, and it's 0 and 1, so it's not both ready. Okay, so I can't execute. So this is a necessary wait. You say, and you're going to be asking, oh, how come there's still a wait? This is the natural thing, because there is a natural dependency between this is the read after write, and read after write, there's no way to resolve it, except just waiting. But then, of course, out of order execution is just moving this. I'm going to show you how you can move this out of the way, so you don't have the rest of them waiting on them until the first execute, and then you execute. So I'm going to show you later how this is done. But then the E3 here, sorry, I haven't done a decode in this stage. So the third instruction to be decoded, so R2 and R6 to be R7. Again, R7, put it to 0, and I'm going to new entry B, R7. So R2 and R6. R2, valid, and no tag, and 2. And R6 is valid, tag, no tag, 6. Okay. So yeah, third cycle, a fifth cycle. Keep executing 3, but then I still can't execute anything, isn't it? Because it's still not ready. How about the next one? Next one is ready and ready. Wonderful. So I'm gonna ready. I got a ready in here, so I can start executing. And you can see that because I'll show you maybe in a bit why is this like available. And then the fourth instruction, I'm going to do a decode. Okay, so the fourth instruction is decoded. So I'm just going to put R8 and R9 into R10. So again, put R10 into 0, and then put this into a C entry. And then R8 and R9 will be valid, 8, R9, 9. Okay, good. Wonderful. And then I also have a fetch here as well. And 6th cycle will be 4. I still can't execute. Do that. And then the next one, can I execute now? Yeah, so valid and valid. And know that I can actually have 2 instructions. So you can see this one I'm using an adder. But this one I'm also using an adder. Why? Because it's 4 cycles, but then your internal pipeline. So if you're internal pipeline, you can utilize every single pipe stage. So in the same time, you can have 4 instruction into the 4 stages of my adder pipeline. So this is fine. Okay, and decode of my 5th instruction, which is what? Multiply R7, R10 to R11. So R11 will be 0, and take this to be Y. And R7 and R10. So R7 is the valid will be 0, and then the tag will be B, and then the value I don't care because it's going to be updated later. And R10 is also waiting, so valid bit is this, and then the tag is in C, and the value doesn't really matter. Okay, so I can see that I now have another blockage of my multiplication. Previously, if we do it in order, it's going to be a blockage, but now it doesn't cause any blockage anymore. Okay, and then now the fetch on my final one. So 7, E5 is still waiting. Do E3, E2, and then okay. My fifth instruction, can I execute? No, because 0 and 0, so I can't do anything about it. So I'm just gonna wait. And fetch, and the final fetch is final decode is gonna be R5 and R11 to R5. So as you can see now, here comes a really interesting part. Is my R5, right? I'm gonna make it to 0 again, and I'm gonna set it into maybe another entry. So here I change it to A to D. So I'm gonna take a very careful here, A to D. Take extra careful here. So you can see that my why do I take extra careful? That's gonna review this operation later. So A to D. So I'm just gonna change my A into D, right? So I'm changing my A to the D. So my newest value will be instead in D. So previously I know that my value is pointing at A, but now my so I'll have to copy whatever is R5 first. So 0. So R5 will be 0, and the tag is pointing towards A previously, and the value I don't care. And then also R11 will be non-valid Y, and then I don't care about the value here. So what happened was, and then I put this entry into D. So in my R5 tag, I used to have A, and then now I'm pointing towards D. What's the significance of that? So if you actually take a look at back into the idea when you have here, my later instruction, it has to be overwriting my previous instruction, right? I can't have the previous instruction overwriting the, if we have the register renaming, right? If you have the register renaming, wait, is that the actual case? Let me think about it. Yeah, so the idea, okay, I'm just gonna put it this way. As you can see here, my A to D, right? I'm pretty much just renaming my R5 to B1. So I'm creating like an extra copy of A and then D, and I have A register here, D register here, and I'm just gonna say that my R5 is instead like a physical, instead like a, not physical, but like, instead like a pointer pointing towards my A and D. So yeah, so as you can see, this is the idea of renaming. So it's no longer like one single register. It sort of duplicates to A, B, C, D, and then I'm just pointing, that sort of thing. So yeah, in this case, I have register 5 pointing from A to D, which is interesting. Okay, so pretty much we've done all the decoding stage, and now we're going to talk about the broadcast. So can I execute in my fifth one? I can't execute in fifth one, so it's fine. I can't execute my sixth instruction as well. Okay, so I'm done. I'm done here. I'm also done here. So remember how when I have the multiplication is done within the sixth cycle and the fourth cycle. So the broadcasting is actually done at the end of the execution stage. Okay. So let's talk about what's execution. So if I'm done, right, over here, this instruction is finally done after all that time. So I will have the results. So I'll have two things I'm going to broadcast, which is X, the other is the results. So results and address. So the result and address is actually really important because first of all, remember how like previously we have like physical memory, which is like maybe R6 or R3 in that case. I'm just going to update it back to R3. But now we have this idea of the renaming. So instead, I will have a broadcasting issue to going back here to go through all the tag and say that, okay, is there any of the tag that is associated with this? If so, I'm going to update my result. Okay, so let's take a look at here. My R3 has the X. Lovely. So I'm just going to update it to be none because I now updated and then valid bit turned to 1 and then the values now become 2. That's beautiful. And then going back here, I'm going to check all the tag, all the tag, all the tag, all the tag. I'm also going to check all the tag here to make sure that is there any dependency on the X. Okay, so let's take a look at here. So I'm depending on X. So I'm just going to say, okay, now the value has been written back. Wonderful. And my value is now this 2. So this is why you can see that there's something called a CBD, the Common Data Bus, or CDB. Yeah, CDB in a Tamasulo paper, because I have this common data bus doing this broadcasting. So pretty much the hardware for this case is I have a bunch of comparator to compare, okay, my address for this X. So I just have a bunch of comparator in each and comparing the tag and also my address after broadcasting. And if so, I'm gonna feed the results into it. So that's what you call the CDB in this case. Yep, so that's done. And then I also need to broadcast my third instruction, which is the add to 7. Lovely. So R2 plus R6. So that's done by having my B, and then my results will be R2 plus. So that's the address. So again, I'm gonna do the broadcasting, just like going through all the possible tag. Like, is there anyone waiting for me? Okay, cool, there is. So if so, turn it to valid and rewrite the data to be 8. And broadcasting here. So no longer waiting for the tag, value will be 8 and turn it to valid. Yeah, beautiful. So now I've done the broadcasting, and then you can see that now 2 things become readily available. So what's used to be not available was the summon instruction, which is the second instruction, which is R3 and 4. 3 and 4. Yeah, so 3 and 4, which is this instruction, right? That wasn't available before, but now it's available. And then also another thing that is available, which is, oh, actually the Y is still not available because I'm still waiting on the C. Yep, but it doesn't matter because I can now have the memory right back, and then I have, do I have the right back in it? Hang on, I forgot. I kind of don't remember whether I need to put an M here, because I think in out of order there's some other way of deal with M, but it's okay, I just put it there. But the second instruction is now ready, so I can start executing it, and then I can also have the M and right here as well. Yeah, so the rest of them I'm still waiting, is it? Yep, so dash dash. Okay, so now I start executing this, but then remember how this stage I also so the fourth instruction, which is R10. So R10 is now available. And again, we have this broadcast from R10, which is the C. So now my broadcast become C, and then what's the result? 17. So I'm going to broadcast everywhere. So again, just going through all the tag and do all the comparator. Okay, so I can update here, which is saying set my valid bit to 1, no longer care about the tag, and then put it to 17. And over here, put it here, which is I don't care about it, value 17. And then, so okay, now my Y instruction is ready, which is beautiful. Yep, so let's keep doing. I'm going to talk about the write back later, because I feel like there's something a bit there's something the in order commit to be happening here. Okay, so and then you have E2, and then now this is memory write. Okay, so my Y instruction, what's my Y instruction? It's the multiplication of 5th, so I can start executing this one now. And for my final one, I'm still waiting, right? So I can just keep going, E4, E2, E3, so that's 9, 10, 11, 12. Okay, so my second instruction is addition. So this is available now. So this is done, this is done, this is done. So 4, what's my second instruction? Second instruction is in A, isn't it? Yep, so is now available, and the tag I'm going to broadcast is called A, and then the results will be 6. So I'm going to go through every single one of them and ended up finding that the only one I'm waiting for is just here. So I'm ready. So I don't draw the whole line because I know that the rest of the thing doesn't depend on. Okay, I'm just going to draw it, but yeah, it doesn't depend on them, so it's fine. So yeah, so this is 1 tag. I don't care about it. 6. Okay, so now so my final instruction I'm still waiting, but then it's okay. And then this is the 13, 14, 15, 16, 17, 18, 19, 20. And I have like E4, E5, E6. Okay, so now E6. So now E6 is ready. So now my Y instruction is available, and then the result is 136 maybe. Yeah, 136. So I have broadcasting Y 136, and I'm gonna go across all the tag. So I'm just gonna be like, oh, going through all here, and then I end up finding that's all the possibility. So now this thing becomes 1, don't care, 136, 1, 136. Yeah, so now the idea is 136 is available. So I have the final instruction finally able to be executing E1, E2, E3, E4, and then right back, memory and right back. So now we sort of condense everything back into the cycle of 20 or 21. So yeah, this is beautiful. And then I finally got the results of my D, which is the broadcast of D, and then 142, and then that will be 1, don't care, 142. And if you actually try to work out this assembly code yourself, you're going to end up finding that all your architectural state is going to be correct. Every single one of them will be exactly as it is, like every sort of value exactly as it is. And so this is one of the very neat example about this. But there is something I still want to talk about in detail about this. So I'm going to go back to the previous example I've done for myself. So this is some of the notes I put down. So first of all, you can see that the one I put here is what I emphasized before, which is notice that the third and fourth instruction, which both adds, are in the same adder at the same time. This is because again, we said that this is done by a careful pipeline stages. So pipeline stages mean that we utilize every single pipe. So I can have like internal pipeline of here, and maybe at this instance I have the fourth instruction, and in this instance third instruction, and they have a pipeline register between them. So it's fine. It's the basic idea about pipeline. So you can't really just do a counter and just like, oh, my adder is occupied for the entire 4 cycles, and then the next instruction comes in. That's not the case. It has to be a pipeline thing. And then the second notation is that just to be careful that broadcast is done by the end of the execution stage, so not to be confused with the write back stage. Third one is notice that E4 and E6 are both updated at the same time. Is there any bus contention? So because that there's E6 and E4. So this is some of the confusion I put for myself last time when I do this example. Well, no, you can dump by just having 2 sets of bus for my 2 different devices for adder and multiplier. So if I just have 2 different devices, then I don't have to care about the data contention that much, is it? And you're gonna ask another question, is that, oh, what happens if I have like 2 bus trying to drive 1 source? That is also not possible because my key value pair, I only have tag pointing at 1 place, not 2 places. So it's like a one. So yeah, it will be a 1-to-1 relation. It won't be a many-to-one or one-to-many relation. No, it will be a one-to-many relation for the broadcast. I can have 1 bus updating all the many sources, but then they won't be the case that 1 source is pointing towards 2 tag. So there's no driving issue. So bus contention can be solved by having another common data bus, so which is fine. So I'll just what I mean was I have like 2 lines and stuff, 2 lines, and one for like adder and the other one for the multiplier. Yeah, that's the idea. Yeah, and then for 5, I'll have the write back also overlaps. what if the data bus so well, in that case you pretty much just have another, so because again you have two different devices, so you have to remember that my adder, right, it can only allow one instruction per pipeline stage. So I can't have, if I have two readily available addition instruction, then I can't put both of them into the same pipeline. So if I have two instruction that is both ready, it can't be like both in E1 and E1. It has to be like E1 and then E1. So in here, when I'm ready to write back, the write back has to be the next stage. So in that case, adder and adder themselves will not be bus contention. So is the multiplier. But then what happens is my multiplier and adder have both write back stage. But that is also very easy to deal with, is by having just two read port or something, like just increase the data bus. So I won't be the case that with one device I have bus contention. I'll have two devices, between them there's bus contention, so I can just put two buses. That's fine. So so fourth one, each cycle start, check that one if the instruction is ready. So I need to check both my valid bit 1 and valid bit 2 to be 1. And secondly, if the instruction has been dealt with. What was that? What was I going to try to say there? Kind of forgot what this question is about. Yeah. So when you are dealing with this, when you are finishing, you probably need to have some. So this is the very simplified version. But then when you actually comes into like, choosing which instruction you have to deal with, you probably need a bit more instructions. For instance, like, okay, I've dealt with A now. What about B? What I mean was like, A is currently in the pipeline, but I don't know about that, do I? I don't know that whether A is already in the pipeline. So I must have another one that's like, am I dealing with this instruction right now? Is it in the pipeline? Something like that. So you have to add some sort of bin extension to say that, okay, this is already has been dealt with already, and then currently, so if my A is currently in here, and I'm gonna check again saying that V is again, so I'm gonna put another A into it. So you probably have to have another one is like, has been dealt with, and then have another zero here, another zero, and then just check that V1, V2, and then not has been dealt with, and just put them all together, and maybe that's the way of doing it. Yep. And then remember that there's also another thing, which is the reservation table itself is like a finite amount of memory. So once you've done that, you have to call the free list. You have to free them. You have to actually, free list might be a different thing. But yeah, anyway, just clear up the table. What's one broadcast reset the entry? Yeah, once broadcast reset the entry. So that's what my 6 is telling you about. So yeah, reset the entry. What about 7? What if add 2 entry wake up and content? So it could be the case that where both of my adder, like both of my A and B are still waiting for Y, and my Y updates, and then both A and B are now ready. So now the idea is like which one to pick. You probably just can pick a random one, or just pick like the first one. Yeah, so you can just like, I don't know, I mean your system very long, it'll probably just be like for loop. It's like, for checking. Once this is done, breakout, and that's it. Just pick the first one. So yeah, it doesn't really matter because out of order actually significantly improves stuff. And the final thing I want to talk about is the idea of write back. So remember that this actually breaks the von Neumann sequential model, isn't it? So there's something called a reorder buffer that I didn't really talk about. So this is actually so now here we are only talking about, so as you can see now you can see that the scale of auto order is actually quite difficult to do, isn't it? So far we only talk about the renaming, and the renaming also as well as the dispatch queue. So far I only talk about that but what about reorder and commit? Okay, so reorder and commit actually comes into another thing which is called the reorder buffer. And the reorder buffer is like a similar structure, but then it's sort of like a very, very similar idea. But then this is what you call the FIFO structure. Yeah, FIFO structure. So the idea is that once you're dispatching, so maybe when you're dispatching your so remember that when we do stuff here. So when you do stuff here, we copy every entry in here, right? The similar idea comes in. Oh, sorry, not this one. The similar idea when you come into the entry here as well. Wait, the similar idea when it comes to the entry, you pretty much just copy everything here and then just write a bunch of stuff here. And then when the entries, when I don't know, when the destination has been written and then when the entry has been written, then you retire this and then write it back to the instruction state. So this is real buffer pretty much saying that, okay, I must have, so if I have something ready here, but then the previous one is probably not ready yet, sorry. Oh, sorry. So when I'm using this entry, I'll put this as 1. And when the destination hasn't been written, that means that I'm still dealing with it. So the broadcast actually extend that you probably need the, I don't know, you probably need the broadcast to be in this line as well. I kind of forgot what the actual operation is. Probably, yeah, you probably need the tag along here as well so that it can be updated in the real buffer. So maybe you have to put an A and something B and something like that. So similar structure. But now the idea is sort of a little bit different. It's like I'm gonna check, okay, is it a 1 here? Well, if it's a 1, that means that I'm ready and then I can retire. But then in this case, right, my previous instruction is still updating, and in the next instruction I am going to I'm ready. But then because the previous instructions hasn't been write back yet, so remember that write back, right? My write back has to be sequentially updated. So my architecture state has to be in order committed, and I'll tell you a reason why it has to be the case. Well, to be honest, if you take a look at what the previous example, you can see that the previous example, in this case, right? If you work this out and then remember how I actually done, okay, something I didn't really do that well, that correctly, is that remember how I have a tag, and the tag goes along this architectural state of my register file. Yeah, so I actually kind of updated already once I do the execution stage. So actually, I think this is actually not the actual register file, maybe. So this is the part I got a bit confused, because if you actually read the paper here, it says something else, which is the where is it? Kind of forgot. There's a case where it calls the physical memory and there's a virtual thing. Kind of forgot where it is. Yeah, so I kind of think it's good to read about this. Okay, multiple queues method, single queue method. Kind of forgot where it is. So there's something called the, yeah, I found it. Physical register file that is larger than logical register file. So your register file, your like standard register file, right, is what you call the logical register. But then you have another thing called the physical register, which is like the renamed version of physical register, which I don't really know that much about. So you pretty much, so probably have to Google chat about, like, ChatGPT about the difference between logical register and physical register. So I'm gonna say that this over here will be a physical register. So they're not the actual. So the definition comes in. You have the yeah. The storage element, that is architectural storage element, namely architect or logical register. So I'm just going to call the logical to be an architectural state. So which is the architectural state is like the actual updated version of it. But then you probably have another physical storage element, is like what you tempered with. Yeah, so you have another broadcasted. So your broadcasting will pretty much be always in the physical storage. And your physical storage is not the actual architectural state. So yeah, just to clear up the thing, yeah, this is the part where I also got a bit confused, which is you actually have two different set of register file, which is why I don't know. Yeah, but there's a physical register file and then also a logical register file. I'm gonna see one example later, but yeah. So what was I gonna say? So there's a difference between the logical register file and then the physical register file. One is like the renamed version, which is the physical register file, renamed version. So yeah, back to the example. I kind of forgot already what I was talking about. What was I talking about? Yeah, but then yeah, oh yeah, this page. Yeah, so your real buffer have to be writing sequentially back. So if this is not available, then I have to keep waiting. So this is actually a circular buffer. So you sort of have a circular buffer that kind of looks go in circles. So ready, good, ready, good, ready, good. So you sort of like retire everything in order and then it wraps around. So I can just keeping so if my order instruction is ready, so I can retire, then I can retire. So now this is free, retire. So my order instruction is now pointing here. So this is why I call this is a circular buffer, because if it wraps around and then you go all the way down and then go back. So that's the circular buffer. And then you can see that now my oldest instruction. So if I'm ready and if I'm the oldest instruction, yeah, I can retire. And let's talk about the in order retirement now. So we kind of see the idea of the out of order commit and sorry, out of order execution and then the in order dispatch. Sorry, in order fetch and out of order execution. But then why do we need this in order commit? So as you can see in this example here, I didn't do any in order commit. So even though this is a logical register file, it still doesn't do anything, right? So if you work it out and imagine that this is the actual register file, every register file will be exactly correct. Then what's the issue? Why do I need an in order commit? It actually comes in, I think the most significant, I think for my understanding, the probably only reason for doing it, but I don't know whether that's the only reason for doing it, is because of the branch. So the branch actually comes in and it's going to be crazy because why is that? Because say that if I have out of order, I have like this instruction, I have this instruction, I have this instruction, and then branch. Yeah. And then maybe the later one will be this. And then I'm going to say that the branch will actually jump to a different address, which is in later. So none of this will be available. But then just talk about if I have a branch, then branch somehow has to be a break. It has to be a breakpoint here, right? What I mean by a breakpoint is like, say that if I don't have a breakpoint here, then what happens is maybe I'll schedule here and I'll schedule here, and then maybe this, I don't know, maybe this one runs first, and then another one probably runs second. I mean the execution part, and maybe this one runs later, and then this one probably runs later. And as you can see, if I commit into my actual register file, now things become really, really messy. And I don't even know where my branch is supposed to do, because this one's supposed to be flush, this one's supposed to be flush. It doesn't really mean to update anything, isn't it? But meanwhile my it has to update, it has to run. And then like when there's an intervention between the later instruction and the previous instruction, now things become quite crazy. So this is sort of the reason why you want the in order commit, so that you can have a checkpoint to say that, okay, this is done, and then I updated, and then I check, and then I execute the next. To be honest, I kind of wink it at the last part because I don't really understand how you can face the branch at this point, but you can find the answer from this paper, which is saying, I kind of read through it, but I just didn't really remember where it is. Yeah, so if you read about the committed state and you have to have a checkpoint, and it's called a history buffer. Yeah, and then you need to have some sort of recovery state, because everything you've done in the commit state is to get rid of the history state, and also you have to update the whole architectural state. Yeah, and then the second method is, so you have to have the checkpoint and the history buffer, which is I explained. But then this is actually not the idea. not the best idea. I think it's because I don't actually know, but the idea is that you can use what you call the physical state and also the logical state, which is before. So the physical state, as I mentioned, is the physical register file, so PRF, and then the logical register file hasn't been updated yet. So the PRF is the one that you do all the broadcasts and all that, blah, 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 and it's updated immediately. And the architectural state instead updated in the sequential program order. And then you need the speculative status of the operation is clear. So like it only updates when I'm really, really sure about this. And the speculative state is maintained in the reorder buffer. And yeah, the space is freed up on the reorder buffer. So basically reorder buffer is like to ensure that, okay, sorry, this one. So like, yeah, I'm ready. I'm ready, so I can retire. But then here, I haven't ready yet, so I haven't retired. And I can't really provide an example when it comes to branch. How does that resolve the branch intervention with the previous thing? Like how does that do the checkpoints and stuff? I can't really work it out, but then maybe I have to read a bit more. But yeah, you can see the idea about that the commit has to be in order, because when I have the branch, how do I ensure that? Oh, okay, that's the correct register and all that. So maybe I need to have a branch instruction maybe at this end of here and saying that, okay, this is ready, so I can check this to register and then I can run it. Something like that perhaps. Yeah. So that's the idea, and then hopefully like you can see how beautiful the out of order is. Yeah. So in the end, everything kind of just looks like this. So where you say, remember how you immediately update all your functional units here, and so your functional units sort of put it back to your reorder and commit, and then I don't know where your PRF should be. But then once you remember how when you do the dispatch, you also put the entry into the reorder buffer, and then the results will be updated for your reorder. And then once you do the commit part, and then you're going back to the actual logical register file, which is the architectural register file, and then update all that. So yeah, thank you for your patience.